No one needed to know.
I got
All right, let's get the show on the road. All right, voices off, please. Time out. Time out. Time out. All right, voices off. Get out your homework. Who's absent?
Hannah and Gabby. I heard somebody.
All right, any questions on the homework before we grade it?
Oh shoot, I forgot my homework. Oh shoot, I did.
What? During course 2, whichever day you are absent, find that day. All right, too many people talking, please.
Oh, Gabby's here.
All right, questions? All right, let's grade this. Here we go. Number 2 is, it says write without exponents. If you put 1 over 10 to the 3rd power, you got an exponent. So they wanted you to expand 10 to the 3rd, 10 times 10 times 10. So 1 over 1,000. Oh, wait, it's number 2. I'm sorry, I gave you answer number 3. Sorry. 1 over 27 is number 2. Oops. Number 4, negative 1 over 243. Number 6 is, well, 1 is just 1. I don't care whether it's to a negative or a positive exponent. 1 to any power, including 0, is 1. Number 8, 1 over 1,024. Number 10, 1 over 16. Why aren't any of these negative? Remember, if the power is even, doesn't matter whether it's negative or positive, the answer will always be positive. It's only when the power is odd that you have a possibility, if you're given a negative base, that the answer would be negative. All right, number 12, 10. 3 minus 2 is 1, 10 to the 1st power is 10. Number 14 is 1. 23 minus 23 is 0, anything to the 0 power is 1. Number 16, 1 over 128. Number 18, 1 over 49. Why are you writing down my answers?
Oh no, I'm not. This is a story.
Number 18 was 1 over 49. Number 20 is 1 over 64. Now, it looked like he was copying down that he was writing something or other. 18 was 1 over 49. 20 was 1 over 64. 22 is 9. 1 over 64. We're on 24. 24 is the number 4. Now, if you put negative 4, they were just asking what n was. There was already a negative there, so just 4. 26 is 0. And 28 is 1. The last one would be negative 8. Negative 8. Jade, make sure you're doing your homework because I'm not forgetting to put zeros into the grade book.
I keep
Oh, it didn't count.
I keep losing my locker.
Sorry.
On the computer, too. I can hear that. It's winter. It's winter.
All right. Listen up, please. Listen up. So I do a poor job of coordinating with Mr. Surratt. He's your science teacher, yes or no, Miss Miss Newburn, I'm sorry. Okay. So I do not know if you had the class on scientific notation yet or not. Have you? Okay, good. So I'm going to be the first. This is something that you're going to be using in science class. You'll have a class on scientific notation every year for at least 2 years. You'll have one here, and we'll get one in a bit more complicated one in Algebra 1. So today's class is something brand new, unless you already know how to do scientific notation. Okay? Brand new. It is the last thing. Boy, does it have some complicated instructions. It has some complicated instructions. Okay. It's done.
Oh my God.
All right. Back up here. So it has some complicated instructions. Remember, on any test or quiz that I give you, you can have a resource card. Some of you will take to this like a duck to water, like this will be pretty easy. Others of you might be slightly confused. You might need 2 days of this. We're only doing 1 day. So what will save your butt is that you're going to put this on a resource card. It's pretty simple. We're going to put a number into scientific notation. I'm going to give you a number in scientific notation. You're going to write it in normal form. It's called standard form. Okay. However, I realize that maybe one class isn't enough for some of you. So what's going to save your butt is you have, not tutoring, is that you have a whole bunch of examples, front and back. You literally could bring this sheet of paper in on Wednesday for the test, and it will show you how to convert numbers from standard form into scientific notation, and from scientific notation back into standard form. So if that is what you need, then make sure you have this. Yes?
Wait, you can actually bring those on the test?
Sure, well, one of them. Most people want to write some extra stuff, so they may need some more, maybe not bring in the whole sheet of paper, but sure, you can bring in the practice test if you wanted to, right? But one piece of paper, okay? All right, here we go. Here is your homework. Now, there is no, you're not listening, you're talking. There is no section 3.8 in the book. It stops at 3.7. I'm calling it 3.8. There is a page called enrichment. It's on page 99. It's scientific notation. Our book doesn't think that you need to know scientific notation as 8th grader. Oh, yes, you do, right? It is a state standard scientific notation. In the big scheme of things, this is not hard. You got to be able to count by ones. Right? But I will tell you, look at how small the text is. These instructions are slightly complicated. Now, I have already written all the instructions for you. You just got to be able to read the instructions and follow along. Here we go. All right, scientific notation. In science, a long time ago, they figured out they had a problem. All science is the application of math to the real world. The problem with science is they typically deal with two types of things, really tiny things or really big things. And the problem with science is you gotta be able to do math with tiny things or large things, okay? So the problem is, well, for instance, if you're a scientist and you deal with stars, astronomers, they have to do math with very, 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 very large numbers. So for instance, the nearest sun is 93 million miles away, our sun, right? Our sun is a star. So the next nearest star, other than ours, called the sun, right? The next nearest one is, right, it's called Alpha Proxima. It's also in our Milky Way galaxy. It's that far away. Okay. If you are an astronomer, oh, by the way, I rounded. If you are an astronomer, you got to do math with this number, right? That means you got to add, subtract, multiply, and divide. If you are an astronomer, you need a large sheet of paper to do math with that number. That's the nearest one, okay? Other scientists, listen please, other scientists deal with the very small. For instance, they deal with water molecules, H2O. They need to physically know how large this thing is. If I measure one water molecule, H2O, it's this wide. Okay, that's in meters. Once again, that is a size that they must do math. They need to add, subtract, multiply, and divide with that number. Scientists learned a long time ago is that they don't want to work with large or small numbers. So they, not mathematicians, devised an easier way of doing math, adding, subtracting, multiplying, dividing with large and small numbers. It's called scientific notation. It allows them to quickly add, subtract, multiply, and divide. Like, for instance, I can multiply these two numbers together in about 5 seconds, right? If I use scientific notation. If I don't use scientific notation, I need a very large sheet of paper to deal with all of these zeros to multiply these two. Okay? So that's what today's class is on. Now, you would think that at the end, I'm going to actually teach you how to add, subtract, multiply, and I'm not. And that's for a different day. All I'm teaching you with today is how to change this number into scientific notation, or this one, and then how to reverse that process. If I give you a number in scientific notation, how to put it back into its original form. Jenna, are you paying attention? Okay. So here we go. The Voyager spacecraft right now is outside of our solar system. So if a scientist needed to know how long it will take, and they need to do this because they got to point their antennas wherever it is, they need to know how long it took for the signal. Speed of light is a speed of light, right? 186,000 miles per second. That's pretty fast, but not as fast as how far this sucker is away. We're talking about a long time for it to send a signal and for it to get back to the Earth, right? This spacecraft is also going at 40,000 miles per hour. They got to put that into their calculation. Once again, it's a large number. Okay? In 1977, which is when this thing was launched, right? Since then, and this is, I don't know when I made this class. I don't necessarily update it every year, but it has been gone for 367,920 hours. So you want to know how far it is away? You got to multiply these two numbers together. A scientist can do this in 3 seconds. And it's not because they're smarter than you. It's because they do this. It's not. It's because they change these into scientific notation. And that's my warm-up for the class.
Donovan, it's jam.
Okay, that's enough of that. All right.
My jam.
So all we're doing today, now listen please, listen. All we're doing today is putting numbers into scientific notation. We're not going to actually do the add, subtract, multiply, and divide. You're going to do that in science class. But you have to be able to put them into scientific notation. Oh, by the way, these numbers are in scientific notation. Oh, by the way, these are the previous numbers that I just showed you, hands down. Okay? So in box number 1, let me explain to you what you're seeing. Right? Just write down what's here in box 1. Scientific notation is a shorter way of writing numbers using the power of 10. And it says powers because it's more than 1 power of 10. The previous numbers had a whole bunch of zeros. There are no zeros here other than that 0 there and the 0 and 10. I've gotten rid of all of the zeros almost. And my claim is now you can multiply these together really quick. And you can. I said it would take you 3 seconds to get to an answer.
Not that one.
Sure, it's 12 times 10 to the 6th power, and I'm done. What's 4 times 3?
30.
Oh,
Oh,
those
wait, 12.
together.
12.
What's 10 to the 16th times 10 to the negative 10?
No, just 10 to the 6.
You just multiplied the previous numbers,
Oh, here we go. Back.
that times that in 3 seconds.
What?
That's why this particular thing is very efficient. Okay, stop and write. Okay, we just multiply those two numbers together and put your hands down. We're not there for asking questions yet.
I'm not
Stop.
asking questions.
Stop.
We weren't gonna do any multiplication or anything, but there is multiplication.
Jaden, why are you still talking?
Because-
All right, write this down. Now let me define, and I don't mean to be rude, but when I say wait till we get to a point to ask questions. A number is in scientific notation when it is written as the product of two numbers. Product means multiply. 2 means 2. Each one of these in yellow, I'm multiplying 2 numbers together. Here's the first one. Here's the second one. You need to write, Landon. Write. This number is being multiplied by this number. So scientific notation is when you multiply two numbers together, but they're two special numbers. Okay? The first number, if you look on both of these examples, the first number will be a number between 1 and 10. Hey, the first number is 4.01. That's between 1 and 10. Hey, 3. That's between 1 and 10. The second number will be 10 to a power. Not 1, not 100, 10 to a power. This is why the definition of scientific notation says it's a way of writing numbers using powers of 10. Genevieve?
So like 0.1.
0 is not in scientific notation. It has to be between 1 and 10. Has to be between 1 and 10. If it's 0 point something, it's not in scientific notation. We good?
Yeah.
All right. So I also need you to put this in box number 1. I'm going to claim that this is a very big number, and I'm going to claim that this one is a very small number. So visually, how do you identify where numbers are in scientific notation, whether they're big or small? How do you figure this out? If the power is positive, it's a big number. And if the power is negative, it's a decimal, very small number. Okay? So we got big numbers and we got small numbers. By the way, this was the distance between us and the next nearest star. And this is the width of a water molecule. 3 times 10 to the negative 10. If you are a doctor and you need to figure out, can you get water inside the human body, you need to know how big a water molecule is. That's why they need to do math with the width of a water molecule. Okay? When you're talking about water moving through a plant system and you have a cell wall, you need to figure out the physical size of a water molecule versus the size of a cell molecule of a plant. You have to do that stuff. There are 2 types of numbers. One is what's called standard form. That's just special words for regular plain old numbers. Hey, that's a regular plain old number. It's big, but it's a regular number. This is called standard form. Hey, here's a very small number, right? It's in standard form. Scientific notation looks like this. This is this number in scientific notation.
I was right.
This is this number in scientific notation. Once again, I get rid of all of these zeros, and I'm left with 2 numbers being multiplied together. One of them is between 1 and 10, and the other one is 10 to a power. Big numbers get a positive number. Here's 2 numbers. One is between 1 and 10, and the other one is 10 to a power. Small numbers get negative exponents. Starting to make a little sense?
Yes, sir.
What?
So,
One of you knuckleheads, go.
Oh,
It's like the 3 Stooges here, except there's only 2 of you.
do you count like the numbers? Like,
We're not there yet, but yes.
I count.
Yeah, if you're asking about why is the number 7, we'll get to that. We're just not there yet. All right, so let's get there and let's explain why that's the case. Now, here are the steps. You agree that it's complicated? Yeah, and they're already in every single problem. Your job now is to read and follow along as I do a couple, okay? So this is the steps for changing a number into scientific notation. Well, let's see how this works. All right, first off, is that a big number or a small number?
big number.
It's a big number. So it says the steps. Step number 1 is to move the decimal place until you create a number between 1 and 10. What in the heck does that mean? Here's what it means. Where's the decimal place at the very start?
Oh,
It's right there. So I need to move it until I make a number between 1 and 10. Clearly, I'm going to move it to which direction, left or right?
Right.
If I move it right, I'm making the number bigger. If I move it left, I'm making it small. I got to make a number between 1 and 10. As you move the number, you're supposed to count. So if this was my pencil, this is what I would do, right? I put it where the decimal starts, and then I start counting. 1, 2, 3, 4, 5. Did I just make a number between 1 and 10?
No.
What's the number now? Clearly not between 1 and 10. When we moved it 5 decimal places, so let's move it 6. Is that a number between 1 and 10? Is that? Yeah. So we just made a number between 1 and 10. Now it's 4.52, and we moved it how many decimal places? So the first number becomes 4.52, and the second number becomes 10. So how many times you moved it? We moved it 7 times. You take those two numbers, you squeeze them together.
Wait, but don't.
No, this is in scientific notation. Yes. Why what? We have a base 10 numbering system. Each time we divide by 10, we move it over one place value. That's why it's 10 and not 100.
Oh, that's a lot.
That's why it's not 9. It's a good question. It's the best one yet. All right. Hey, big or small number? All right. The decimal place starts right here. So we simply count 1, 2, 3. Is that between 1 and 10? Is that between 1 and 10? That's 4. Why'd you say yes? It's 12.7. Is that between 1 and 10?
Yes.
You moved it 5 times. So what's this number now? 1.27 times 10 to the 5th because we moved it 5 times. Okay, here are all the steps. When you actually do it, it's not as complicated, but those are the steps. Yes?
So what did you do for the number like it was like 0, 1, 0?
0, 1, 0.
Like if like take that same number, but it wasn't like 0, 0, 0, 0, 1, 0.
Oh, we still, you mean like if there were numbers here as well?
Yeah.
Yeah, you will do some rounding. Generally speaking, it's a good question. He says, what happens if it was 1, 2, 3, 4, 5, 6, 7?
Yeah, that. Yeah.
So we would still move it, let's see, 1, 2, 3, 4, 5, 6 places, right? So that would be 10 to the 6th. And we generally round to the first 10th. So maybe 1.2 times 10 to the 6th. All right, good question.
Wow.
Hey, Donovan.
Yes.
Please only make noises that are conducive to classes.
Okay.
All right, here we go. Hey, big or small number? Why am I asking you whether it's big or small? Do you see what it says for these two steps? If it's a big number, the exponent is going to be positive. If it's a small number, the exponent is going to be negative. Okay, so all we got to do is count decimal places. Well, let's see, that would be 1, 2, 3, 4. I moved it 4 places. Squeeze those two numbers together. Oh, by the way, that was box 2. Did you beat me to the answer?
Yeah.
Okay. Do box 3, please, all by yourself. So what we generally do is we generally tend to round at the very end. What? Just count. Yeah. Agreed, but move the decimal place first. 1, 2, 3, 4, 5, 6. Now, you see how you put loops? I would encourage you not to do loops because you almost made a mistake. If you put dots, you're not going to make any mistakes. 1, 2, 3, 4, 5, 6. You started to make loops, and then you kind of like almost went past them. You know what I'm saying? And then rounded 3.2. Okay, we'll check here in a second. Who needs help? Anybody?
I knew I was right at the beginning. It has to be something
Jonathan, you gotta come back to school so they play with your dangle stick.
Boys.
Yeah.
I'm the more little kid.
You might do it right now.
Randall got no socks on too.
I got socks on.
They're small brains. Small.
Seems like I got big socks.
There you go, that's like,
And the reason is that we say that in the
The
grand
ones that
scheme
they
of
give
things,
you
it's
to-
hands
If
of
you
the
can't put on for free,
or
we
that
get
that's
on my
210.
Yeah.
I just
Like, so it'd be like,
It wouldn't be, you would just
Everybody's
change
gonna go.
You would skip the 9, 6.
Donovan.
Just three.
Donovan.
All right, now look at the board. So the number one question was, okay, everybody moved it. Everybody said that there was 10 to the 6 power. The question is, what we tend to do is we tend to ignore all of that, and we simply say 3.2 times 10 to the 6. Okay? The job of scientific notation is two things. There's a little bit of rounding involved, and then the second thing is we want to make the number easy to multiply. If we leave it as this, it's not pretty easy to multiply, right? Our whole purpose of this was to make it easy to multiply. Yeah.
like, well, what do you do when it's not between one and zero?
You got to give an example when it would not be between 1 and 0. Well, we haven't, that's the next ones we're about to do. Second one, 1.2 times 10 to the 9th power. So it turns out billions are to the 9th power. Questions on changing large numbers into scientific notation. We feeling confident?
What about 6 trillion?
Trillion would be 10 to the 12th
So
power.
6 billion.
How many zeros?
About like 50.
All right. So Genevieve's question is, well, what about decimal numbers? Well, decimal numbers, large or small? Small get negative powers. The process is still the same. Are you paying attention? Okay. The process is the same, except this time, instead of going to the left, we're going to the right. Notice it already has a decimal spot. It's already there. All we got to do is count. So if I move it one place, is that a number between 1 and 10, Genevieve? If I move it 2, is that between 1 and 10? If I move it 3, is that between 1 and 10? If I move it 4 times, what does it literally say right now? And you're saying 3.4 is not between 1 and 10. What is it between them? Oh, you're saying it is between 1 and 10. So once you find that you've made the number between 1 and 10, you stop. You got to remember how many places we moved it 4. And then you have to remember that small numbers get negative exponents. So this would be 3.4 times 10 to the
3rd power. 4th power.
absolutely 100% wrong.
Negative.
Because
Negative 4.
small numbers get negative powers.
I knew it.
Okay? To the negative 4. Good? Let's see another one. Really small number. Really small number. Gabby, whatever you're doing, please stop. All right. I don't know. Here we go. Hey, we're moving this one to the right. And we're trying to make a number between 1 and 10. So count along with me. 1, 2, 3, 4, 5. And I stop because that's a number between 1 and 10. Yes?
One more.
One more? What's the number now?
5.4, which is?
That's between 1 and 10. So 5.46. Now, how many times do we move it? Secondly, I want to point this out. Everyone that I've looked to, maybe because you've had this class before, was doing it with loops. And both people that said, watch me do it, got it wrong. Because when I saw them do loops, here's what they did. They went loop, 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 loop. They skipped over. Loops are not very efficient. Take your pencil point and touch between the numbers like you're actually putting in decimal spots, like I'm doing right here. This would be me touching it with my pencil. 1, 2, 3, 4, 5, 6. And my claim is that if you do it that method, instead of the loops, I'll just say I was taught using loops, and I've screwed this up more times than I'd like to admit because of until I started switching to touching between the two numbers. I think it's more accurate. So we moved it 6 places, but it was a small number, so it's not a positive 6. it winds up being a negative 6. So 5.46 times 10 to the negative 6.
This was easy.
Yes?
Yes.
All right, let's do one together. Here we go. Box 4. Take your pencil. Let's count decimal places. Let's see. 1, 2, 3, 4, 5, 6. I'm getting 7. Is that what you guys got?
Yeah.
So that's 9.79 times 10 to the
Negative.
times 10 to the negative 7. Yes?
Yeah.
His mama. What do you do?
Hey, Donovan, keep your thing on mute, please, unless you actually have a question.
No.
Oh, here you.
All right, do box 5, please, all by yourself. Box 5, all by yourself. Box, check with your question.
All right. They're all right.
Yeah, keep going.
Wrong. That was
7,
wrong.
I'm sorry, 6.7.
That was wrong, my guy.
6.7 times 10 to the whatever many times you need. Yeah, we're just doing some rounding. Well, the ones that have all the extra digits, just do some rounding. You got this record? Got this record?
Oh,
You?
I don't want to be wet.
Take it out of context.
No.
I'm trying my best.
Don't forget, small number, negative exponent. Small number. Hey, you're supposed to be doing your work.
I am doing my work.
No, you're talking. Do your work. Yes.
I'm doing my work.
All right, let's check our work. Here we go. The first one, Jenna, what you get? Say it. Just talk, Jenna. You got this. What do you got?
2.3.
Stop, Jaden. What happened to the 6 and the 7? So, Jenna, the steps are, look up here. We move the decimal until we make a number between 1 and 10. If I move it between 2 and 3, you make 672.33. If we move it until we get a number between 1 and 10, that would be right there, 6.7233. We do a little bit of rounding. We say about 6.7. We moved it 4 places, but it was a small number, so it becomes negative. Once again, these 2 numbers right here, we would leave off. So 6.7 times 10 to the negative 4 power.
Oh, I'm all the way down.
Yeah. And if you leave those extra numbers in there, technically it's still in scientific notation. It just doesn't make it easier to multiply. Yes.
So is it always going to be like times 10?
Always times 10. Right? Always times 10. Second one, that's a lot of zeros. If we continually move it across, we get 1.2 times 10 to the negative 10. Yeah. Caden. Stop. All right. We got to do 2 more things. Now we got to reverse the process. Now I'm going to give you, so you got to switch your brain. I'm going to give you a number in scientific notation. You're going to put it in standard form. Now, Jaden, are you listening? Okay. I'll get some students that think they can figure this out simply by looking at the power and saying, oh, that must mean I need to add 6 zeros. That is not the case. That is not the case. The 6 doesn't mean how many zeros. Guess what the 6 means? How many decimal places to move it. The point I'm trying to make is that this 6 does not mean how many zeros. Jenna, are you listening? You see the 6? It does not mean how many zeros to add. Why am I making a big deal about this? Because there are a bunch of kids out there that every single year, that's all they do. I don't know, 6, it must mean 6 zeros. It doesn't. It simply means move it 6 decimal places. So here are some steps. Are you listening?
Yes.
Hey, today's class isn't going so hot. There's too many people talking. Okay? So I'm going to give you my interpretation of it. You won't see this in the book. This is my interpretation. All right, you got to pay attention right now. Does this mean big number or small number?
Big.
Now let's think this through. Are you thinking?
Yeah.
Where are the zeros on a big number? To the right or to the left?
To the right.
You sure?
Yes.
Okay, so before I move the decimal place, I want you to put in, what does it say? It says put in a bunch of zeros, not 6, a bunch. No, don't add 42, right? But I want a bunch of zeros. Here's the issue, look at me. The kid that doesn't put in the zeros ends up saying, well, I got to move the decimal place. So they move it once, twice, and then they're kind of like touching the screen or their paper. They don't know how many zeros to add. So I want you to initially add a bunch of zeros. You told me a big number has zeros to the right, so I put the zeros to the right. Now I have room to move the decimal place. If you don't already have the zeros there, what happens is you think you're putting the right number in there, and you end up not having the right space. So how many decimal places do I need to move it? So I move it 1, 2, 3, 4, 5, 6. Erase those extra zeros, and whatever's left is your actual answer. Now it would help if you put a comma or two just for clarity. You don't have to put a comma, but it would help. All right, let's see that again. Hey, big or small numbers?
Small.
Are you paying attention?
Yes.
Big or small numbers?
Small.
How do you know it's small?
Because it's negative.
As a negative. Now think this through. On a small number, do the zeros go on the right or the left?
Left. 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 Left.
On the left. So for small numbers, the zeros don't go to the right, they go to the left. Once again, I'm adding a bunch of them, not 42. Just enough so that I can move it how many places?
3.
Once again, the 3 doesn't mean how many zeros, it's how many decimal places to move it. So I'm going to move it 3 decimal places, in this case to the left, because it's a small number. 1, 2, 3. Get rid of your extra zeros, and there's your answer. Okay. All right, let's do box 6 together. Here we go, box 6 together. All right, first number, big or small on the left?
Big.
How do you know it's big?
Because it's not negative 6.
Because it's a positive exponent. So add a bunch of, it's not 6, right? I'm not adding 6 zeros, I'm adding a bunch. Now we're going to move it 6 decimal places. 1, 2, 3, 4, 5, 6. And we wind up with 5,560,000. Hey, check it out. It said 6, and we only have 4 zeros. It's not the same number of zeros.
I didn't get that.
What?
The number was 6, and we only wound up with 4 zeros. I'm just pointing out that the 6 doesn't mean how many zeros are in the number.
So you don't count that like that. You don't count that.
What do you mean you don't count what?
I said like 5, 5, 6. I went off that.
Right, but I'm saying the 6 means how many decimal places to move it. So once you add a bunch of zeros, then you move it 1, 2, 3, 4, 5, 6.
I added like
I have no idea what you're asking.
so like I added.
What do you mean added?
I went from this thing. I started on that.
Oh, good point. No pun intended. Hey, listen. Occasionally I get a student that does this. Watch what I'm going to do. When they move, they go this. They go 1, 2. They start at the decimal point. You never start on the decimal point that's there. You start on the next one as your first count. So your first count is after the decimal. 1, 2, 3, 4, 5, 6. Thank you for bringing that up. Yes.
Would it be like for a shortcut?
No shortcuts.
No, please.
No shortcuts.
No.
All right.
Yeah.
Second one, big or small number?
Big. Small.
Yeah, it's a negative 10, so we need to add the zeros to what? The right or the left? Small numbers have zeros on the left side. Big numbers have zeros on the right side. So you gotta have that solidly in your brain when you're thinking this through. Caden and company. All right, one of you move up front, please. You guys you're just messing around with your partner there. All right, we need to move it 10 spots. Remember, if we were to move to the right, you're making a very large number. So we're going to move it to the left 10 spots. If you move it to the left 10 spots, That's what you wind up with, a very, very, very small number.
I almost said big numbers.
Scientists do math with this number. However, they write it in scientific notation so it makes the math easy for them. Yeah.
So with the decimals, would you be able to take off the 2 from the 6? So for the 5.
No shortcuts. Do box 7, please. Do box 7, please. Yes.
Oh, it seems like it's because if the number of zeros you add are more than that, then you know it's going to be 26.
Yeah, and the nice thing is if you do put that number of zeros on there, you're always guaranteed you will have space to move the decimal. So for me, would it be, I'm not saying the final answer, I'm saying before the answer, I'll go ahead and put about 7 or so zeros just so that I have room to move my decimal place. I'll put in about 5 zeros just so I have room to move my decimal place. And like I said, I see plenty of kids that don't want to put the zeros and they just put like these silly little loops on the bottom and somehow they think they'll be able to put the right number of zeros. Inevitably, those loop methods mess them up and they don't put the right number of zeros. Anybody need help?
Yes, sir.
All right, the first one ends up being 86,400,000. The second one ends up being a very small number. Let's see if I can figure this one out. Tenths, hundreds, thousands, 10,000, 100,000, million, 10 millions. So 114 10 millions. That's crazy small. 114 10 millions. Only a scientist would deal with a small number like that. As a human being, like I'm going to the store, Home Depot, and buy something, they don't sell things in the 10 millionth size, right? They sell things in the tenths or even the hundreds or sometimes even to the thousands. So that's kind of where they stop for measurement of physical things.
10 millions.
No one except in the scientific world deals with something that small. If you're building something like the people that built this Expo marker, their machines, they typically measure to the 10,000ths, and that's pretty darn accurate. I bet this is only measured to the nearest 100. I'm guessing, I don't know for sure. Yeah.
If we're just going to the grocery store, when would we use it?
If you are a grocer, you might use this scientific notation, but as an individual, you would never use this. You're only going to use this. You're only going to use this if you're dealing with large or small numbers where you need to add, subtract, multiply, divide without a calculator.
By the way, that's one of the best.
All right, yes.
Right, but what if I need like 1/16 of like a fraction?
Right, and I'm saying that thing, even that can be done pretty quickly. The other thing too is that your calculator only has so many place values. Oh, no, by the way, you've seen scientific notation on your calculator before. You just didn't realize it. So for instance, if you take your calculator, you've all done this, I know, and you turn it on and you just put in a bunch of 9s and then you say times, I don't know, 4, 4, 4, 4, 4, 4, 4, 4, 4, and hit enter, your calculator will write in scientific notation. It doesn't have enough things. It puts the letter E to represent exponent. And so it says the answer is 4.4 times 10 to the, read it, 4.4 times 10 to the, the number's right there,
Wait.
to the 36th
Oh, I
power.
thought you were having your off the board.
It also does it with very small numbers. If I take 0.0001 and divide it by, I don't know, 1,500 or so, it puts the number in scientific notation again. So what's the answer? The whole answer, 6.6 times 10 to the, so your calculator will write in scientific notation. That's what you've been seeing all these years. All right, last thing, this is new, okay?
What? I could do that.
That's nothing to do with
I would like to see you try.
I bet you God they could do that.
Listen, please.
Donovan, you
Listen.
do that.
Has nothing to do with anything. All right. It's called trial riding, and you fail if you touch the ground with your feet. So you have to go over all the obstacles, and you can never take your feet and touch the ground.
Let's do it.
All right. Is this number in scientific notation? Yes or no?
Yes.
Why is it in scientific notation?
Oh, no.
Oh, watch it change your mind. So occasionally you get numbers that kind of look like they're in scientific notation. Jenna, are you paying attention? Sometimes you'll get numbers that appear to be in scientific notation. They're not. So if I ask you to put this one in scientific notation, well, let me show you what you would have to do. Well, it looks weird. It's not what we're used to. So here's how it's done. You ignore the times 10 to the fourth, and you just look at that number. Is that number in scientific notation?
No, because it's
Let's
more than
Put it in
10.
scientific notation. Is it big or small?
Small, big.
Big. So how many decimal places would I have to move it?
One to the left.
So that would be 7.86 times 10 to the,
Fourth power.
how many times did you move the decimal place? So 7.86 times 10 to the first, but what's underneath my hand?
Fourth.
Times 10 to the fourth. Well, what's 1 plus 4? So here was the start. Here was the finish. What's the rule? Here was the start. Here was the finish. What's the rule?
Move it once to the left and once to
Well, that's not the rule. Move it once to the left or right. What's the rule?
turn it into scientific notation and then add the two notations.
Give me an easier rule. What's the rule?
However many times you use the decimal, you add it to your.
If you start with a big number, what's the rule? What you said. If you start with a big number, then
You just move it. However.
you increase this number by,
However many times you use the decimal.
if it's a small number,
You increase that by.
you decrease it by how many times? I'll say this again. If you start with a large number, then you're going to increase this number by how many decimal places it took to move it. How many decimal places did it take to move it? Once. We only moved it one time. That's why this 4 now becomes a, if this was a small number, then you're going to decrease the power by how many decimal places you moved it. Okay? Big or small number?
Big.
Are you paying attention?
Yeah.
Some of you aren't.
But it's
Maybe. If this is a big number, yes?
yes.
How many decimal places will we have to move it?
Twice.
So this 3 now becomes a,
2, 1. No, five.
becomes a 5. Big numbers, we increase the power. Stop. If it's a small number, we will decrease it. What's the math behind it? Well, if you put 312 into scientific notation, that would be 3.12 times 10 to the second power, move it twice. Include the times 10 to the third, and 2 plus 3 is 5. But the general rule is this: if the number is large, count how many places you moved it, increase the power by that many places. Hey, box 8, big or small?
Big.
So, is this number going to increase or decrease?
Increase.
You are now taking his role of saying the wrong answer every single time. All right, how many decimal places?
3.
So therefore, that becomes,
Oh, 12. Oh, no.
11.
all right, so final answer,
It's
1.23. Let's do a small one and then we'll go home. All right, here we go. Look up here. Stop what you're doing, look up here. Big or small number?
Big. Small.
That's
One more
small,
word.
but that's big.
Hey, how many decimal places would you need to move it? So this 8 now becomes a,
6.
wait, we gotta stop. We gotta stop. We gotta stop. Okay, now everyone, mouths off. Let's think this through one more time. You start off with a big number. The exponent increases or decreases?
Increases.
If you start off with a small number, is the exponent going to increase or decrease?
Decrease.
And it decreases by how many? Where are you getting getting a 3 from?
Because there's 3.
Yeah.
1, 2.
Oh, I keep counting.
So this becomes a 6. So 6.4 times 10 to the 6. All right, key parts.
Donovan, you gotta come back to school so they can play with your dangle stick.
Yes.
I forgot that.
How many what?
Wait, is Donovan still on?
2, I believe. Maybe it's 3, 2 or 3.
Is Donovan still on?
We're not talking to Donovan. No. Yes, I'm listening.
Bye, Donovan.
I still want this, but I forgot to give this.
Oh, thank you.